Now, in looking at the given algorithm, at any given algorithm that we have for a classical computer to use, a number of ways and a number of concepts and questions that arise include oftentimes the wonder of how does our algorithm behave, and more importantly, how does our algorithm behave as the size of the input grows larger and larger? Because the thing is, computers, of course, are exceedingly useful for these tasks and making them easy, right? But what's the point of using a computer for even the smallest of things? They become especially important when the size of whatever data or how many items you're trying to input into your computer become larger and larger, because then beyond a certain point it becomes almost impossible for a given human to calculate on by hand or on their own in a timely manner. And so we want to figure out, how does our algorithm behave as the size of our input? We'll call the size of our input n. Size of input equals n. So as this approaches infinity, as it gets larger and larger. And so we can illustrate this in several ways, and let's use a sort of graph here, and we'll put the size of the input n on the x-axis, and we'll put what is known as the running time on the y-axis. The running time. And the running time in this case is a useful way of analyzing how this, right, your algorithm will behave, in the sense that we can consider how long it takes for this algorithm to run through and calculate or process all this data. And so let's say we can describe the running time in terms of your input using some function f of n. And if you're unfamiliar with this sort of notation, this type of function notation, essentially what it does is this f here, and let me use a different color, this f here names your function, and here this n, whatever is in this parentheses, essentially represents a given input. Now, of course, it is worth noting you can put a function inside of a function, such as f of g of n, right? And basically what we're doing is we're taking whatever's inside the parentheses, this g of n, right? And if we break it down a little further, we're taking this n, we're plugging it into g of n, we're taking this output and we're plugging it into f of n. And so basically that's the general concept behind function notation. So if we represent the running time of this function f of n on this graph, let's say it looks something like this, right? And it doesn't have to be perfect. And the concept is, however, that over time, as your n increases, as it gets larger and larger, as it goes off this graph, essentially, what we're seeing is that we can start describing the general behavior of this graph using, more general terms. And you can see the issue a lot of the times with understanding the exact running time of our algorithm is that the more complicated our algorithm becomes, the more complicated it becomes to represent it. And so what exactly do I mean by that? So we'll start off with a bit of a basic, kind of very rudimentary instance. So let's say we want our computer to calculate 1 plus 1, right? And on the side we want it to calculate 3 times 4. And let's break this down into 2 pieces. So 1 plus 1, right? 1 plus 1 is quite straightforward. It's addition. And so we can clearly and very confidently say it takes some constant amount of time. And we'll call that Ka, right, for addition, A for addition, and that's how long it takes for you to add these two elements. And now if we have multiplication, on the other hand, let's say it's Km, right, M for multiplication, that's how long it takes for a computer to multiply these two numbers. Of course, things are a little bit more complicated on the actual level, but let's just say for some case here, that's how long it takes for it to multiply two elements. Now, that's quite easy to see, quite straightforward if we just had a very basic algorithm that added 1 plus 1 and maybe it multiplied 3 times 4. But the thing is, when we start taking variables, when we start taking data and these sizes, right, of n, and we start considering them, all of a sudden taking into account these exact values, exactly how long it takes this computer to process this information, makes things so much more complicated, because we'll end up with some crazy function that takes some constant, right, k of a times, some function f of n plus k of m times, some function g of n, etc., right? And maybe it's even raised to a power, etc. if you use maybe like if and then statements, and which are basically loops. And so things get so much more complicated that we need some general notation that does not go into this craziness, that does not devolve into using different constants for every single possible operation that there is. And so I digress. Let's go back to this concept of asymptotic notation. Let me make sure I can spell this correctly. And now let's begin by taking our graph, right? And let's consider how can we simplify the way that we illustrate f of n. How can we simplify the way that we consider this, right? And one way that a lot of people have done, and if you've taken maybe algebra 1 or algebra 2, is that they've taken a general sort of concept. If you have some polynomial functions, such as, and let me write this on the side, such as 2x, that's y, equals 2x to the 5 plus, 3x cubed plus 4, right? What ends up happening and what's interesting is that as your x here approaches infinity, we can start describing this as approximately equal to 2x to the 5, because in the long run, right, these two sort of items back here kind of become things you can ignore because they're so much smaller than x to the 5. If you take infinity to the 5th power, this is way larger than infinity to the 3rd power. And I'm saying infinity in terms of just some really large number, not actually infinity, just to clear some things up. And so we're going to do something very similar here, similar to what we do in algebra. We're going to be taking a given function, and we're going to be giving it some sort of bound. We're going to be describing it using some simplified function. And what we're going to do here is that we are going to take an upper, right? This is your upper bound, and we're going to take a lower bound for your function, lower bound. And to make things a little bit more straightforward, we're just going to say this is an upper bound and a lower bound for the function as n gets larger and larger, right? So maybe at the beginning, your lower bound could actually be a little bit higher than f of n, right? Right here, it can be higher than f of n, but in the long run, your lower bound will actually just end up being lower than f of n. And so, on that note, let me shrink this sort of illustration that we have here. On that note, we can begin considering types of notation. So we'll start with the upper bound that we have here, and we'll call this big O of some function g of n. Right, and this is not a formal definition of it because, once again, we're just doing a general analysis of the algorithm that we have, right? But what big O of g of n essentially does is it says that for some function, right, big O of g of n, over time, as it increases, we're going to have some constant that exists that can multiply by your given function inside big O, and that over time it will be larger, it will create an upper bound for f of n. That is, for some constant c, for some real number c, times g of n, it's going to be greater than f of n as n approaches infinity. And the same thing may be said for the lower bound, and this is what we're going to be calling, let me make sure you can, this is associated with this. All right, and so what we have here is a lower bound, and it's basically an uppercase omega. And I apologize, I have very bad handwriting. That's an uppercase omega for some function. We'll again call it g of n, just, for consistency's sake. We'll go back to it a little bit later. In this case, similarly, you can have some constant, right? And we multiply again by that whatever function we have in there, whether it be like log of n or n squared or n cubed. It will form a lower bound for f of n, right? So we can guarantee that it will be lower than f of n in the long run. right? And to put that in other terms, basically what we're saying is that for some constant c times g of n, fundamentally it will be less than f of n, right, as n approaches infinity. And so now that we have these upper and lower bounds, is there a way we can continue to simplify these bounds, a way we can continue to simplify this description that we have of our algorithm, right? Keep in mind f of n here is describing our running time of our algorithm, and there is indeed, and it is what is known as theta of some function g of n. And so this actually gives both an upper and lower bound, because what it essentially says is that for some function g of n, right, for some function g of n, again, some function g of n, if I take a constant c1 and I take a constant c2, and if I multiply it by g of n by c of c1, right, and then multiply that function, it forms your upper bound. And if I take that same function, if I take g of n again, and then multiply by a different constant, c2, it will form a lower bound. So in this case, they're going to behave the exact same way, right? But just, stretched slightly differently. And so that's the concept of theta of n. So theta of some function. And it's quite neat because it creates an upper lower bound and it gives it in those terms. And so we'll be going to a little bit more complicated example probably a little bit later, but just for understanding exactly what we have here, let's take this simple line of code for some value I, right, 0, and I is less than n, and we'll interpret this in a second. I'll just use +1 here. Print I. Print I. Alright, so this is kind of not a formal instance of code. So a little bit closer to the side of pseudocode, it's definitely not, the neatest way you can write it. But what this statement here, what this code here is saying is, let's say n, keep in mind n is the size of whatever input, let's say n is 5, right? And we'll start out with I equals 0, and this is just your starting point. Start here, right? And so when I equals 0, so this is I, right? This is your output. So when I equals 0, right, then we print out whatever I is. And so we print out 0. And then, of course, we add 1 when we come back, right? So then that would be our next step, step 2. So this is 1. Step 2, right, we add 1, and so that becomes 1. And then we take this and we compare and we consider the bound, the boundary, the limitation. Is I less than n? And in this case, n is 5. Is 1 less than 5? Yes, it is. And so we say, we print I, right? We take whatever is inside this little loop here. And this is a for loop, by the way. And we output 1, we print out 1. Similarly, we again go back, right, and we loop back to step 2, and we say, okay, 1 plus 1 is 2, and is 2 less than 5? Yes, it is, and so we're going to print that out as well, and it goes on from there all the way up until we reach 5, where I equals 5, and is 5 less than 5? The answer is no, and so the very last, output that we have is 4. Alright, and so basically that's what our very basic line of code does. And so if we take what we said earlier about theta of n, and let me use a different color here. What we said earlier about theta, right, theta of some function g of n. Right, we want to figure out what g of n here is. And so we want to give it an upper and lower bound using the same function. And so what we can do is we can take this and analyze the exact algorithm that we have. And so let's consider this for loop. And how many times will this for loop run, right, based on, whatever size of our input is. In this case, our input size, again, is 5. Well, what we have here clearly is the case where what we're considering, which is 5, right? And so, but then again, let's put in terms of n, so in terms of variable, of a variable. And so clearly it's going to be O of n, right? Theta of n, I'm sorry. So theta of n, because it's going to run it a total of 0 all the way to n minus 1 times, which is actually a total of n times, right? And it's going to run this for loop a total of n number of times. All right, and let's consider how long it takes for it to print out that statement. And printing it out is just going to take some constant amount of time, because it doesn't require, and it's not dependent on how many and how big your input it is. Essentially, it's just printing out a single number each time. So actually this is theta of 1. And so because it's a for loop, we're just multiplying a constant by n. So actually the running time of this given line can be described as theta of n, right? And so basically that's it. That's the general concept of asymptotic notation. This is a very simplified form. If you're a little bit confused, don't worry. You can always check out the qmunitytech website and double check and loop back on any notes that there are. Long story short, we're just trying to describe how long it takes for this general algorithm to run based on its size. And what we've said here is that there's going to be some constant out there where it's going to just run. And this will describe your running time of this for loop here. And of course, once again, it might vary depending on what classical computer you have. So remember, that is all for today. Just remember, stay curious, keep on learning. And if you have any questions, just don't hesitate to just go and be curious and keep searching.